Hello dear student, I am Model Islam. Today in this video we will discuss detailed theory of countability and uncountability. Okay, so without delay, let's start. Okay, I have uploaded 5 video of PHP solution of countability. Okay, and today we discuss the brief theory of countability. Okay, and that needed. Okay, I have written this in previously. Okay, but that time I can't upload the video. There is a problem in laptop. So without delay, let's start. Okay, so since it's written, so I think it will take very few time, okay, to discuss. So let us start. Equivalent set. Do set A and B are said to be equivalent. You can set two set A and B are said to be equivalent. Okay. If there is mapping F from A to B, there is a bijective. Okay. Two set A is said to be equivalent, or you can say equivalent if there is a bijective map between these two sets. Okay. Bijective map means it is one map and one map. Means it is injective map and surgery map also. So injective map means this component hold either x not to y, this simply f is not to fy, or if is equal to fi, this will give x equal to y. Okay, these two conditions happen, either this happen or these two happen. You can say f equal to fb. Okay, you can say or if you want to means it is ontoness, then range will be f equal to b. Range, if means range na, range will be b, range will be codomain. Okay, now can you give me some example of equivalent set? See, in set of natural number n with set of even natural number, these two are equivalent because there is a mapping. You can say fn equal to 2n. This is an injective map. If you compute fn equal to fm, then this is 2n equal to m, na? So this is n equal to m. So it's injective. Okay, and this also fn equal to 2n equal to n. So this gives the map is onto also. Okay, so this map is injective and onto. Okay, so you can say this is bijective. So this set n and e are equivalent. Okay. Now you can say interval same type, also the interval different type also are equivalent. Okay, now n z q this set are equivalent. Okay, n z this set equivalent. Okay, we will discuss this in the next part. Now enumerable set is set to a set to enumerable if it there is mapping from n to this set, that may be bijective. Okay, say mapping a set to enumerable if there is mapping from n to this set, this is bijective. If bijective, this set same current na, so current will be a will be current n and current n is alif naught, so this current a will be alif naught. And you can say one more thing, that if f is mapping from n to a is bijective, then inverse mapping f equal to f inverse a to n is also bijective. Now a and z q, these are example of inverse set. Okay, this both set all set are currently alif naught. Now countable set, it says a subset of R is said to countable if it is either finite or enumerable. Okay, it says set to countable either finite, means the finite set will be countable if it is single set one. Okay, this is also countable set. Okay, if it is single contain n element 1 to n, this is also countable set because finite set is countable. And also inverse set, this inverse set also are example of countable set. Okay, so a set is set to enumerable or denumerable. Sorry, a set is countable if it is either finite or enumerable, or you can say it is enumerable. Okay, so finite set are countable set and enumerable set are countable set. Now uncountable set is set to uncountable if it is not countable. Okay, so there are some example of uncountable set. Say R, set of real number. This is set of real number. Okay, set of all real number. So one set of real number uncountable set na, this is uncountable set. Set of irrational number is also uncountable set. Okay, but set of rational number is countable. Okay, this set of rational number is countable, but set of irrational number is uncountable. Now we have discussed this in the previous video. Set of all function from n to 2 and set 1 to. Okay, this current will be current b per current a. This is our a and this is our b. So current b, current a, current b is 2 because 2 is 2 element. So 2 per alif naught, because current natural number is current alif naught na, current natural number will be alif naught. So 2 per is continuum, so this gives uncountable set. So this is uncountable set. See, if it contains 3 elements, na, 4 element, 3 more than 2 element, this is also again uncountable set. I am saying that if it set contains 3 element, if maybe from n to 3 set 1 to 3, this is current will be 3 per alif naught, and 3 per alif naught you can say greater than 2 per alif naught, because 3 is greater than 2 na, 2 per alif naught is C continuum, so this set is current greater than continuum, so this must be uncountable set. Okay, so this is also uncountable set. In the end, you can say if it is mapping from, you can say, I'm writing here, if in general you can say if n is mapping from natural number to that set, a set, and a is current greater than 2, then this gives, if you consider the set of all mapping, this consider the collection of all those mapping, then this gives a set having cardinality uncountable, because if it current to a, current of n. Okay, now current, this is greater than 2 na, so you can say it is, suppose it is limit m, where m is greater than 2, so natural current is alif naught. Okay, m is the coordinate of a, I am assuming. Okay, now m is greater than 2, current is greater than 2, so m is greater than 2, we can say greater than 2 power electron na, 2 power electron is quantum, so 2 power quantum, so this is current greater than quantum, this set is current greater than quantum, so this must be uncountable. So in here you can say if is a mapping from n to a where a is current greater than 2, then this set must be uncountable set. Okay, now example of some countable set. We all know n, z, q, this set countable set, na, this set countable. So if you make finite constant part of countable set, if you make n cross n, this is current of n and current n, because there is property current of a cross b is nothing but current of a cross current of b. Similarly, if you make n times product current of a cross current of n cross to current n, this gives current of n current of n. So current of n will be current alpha naught, and current alpha naught, if you make alpha naught for n is a finite decimal number, so this gives alpha naught again. Alpha naught, if you current alpha naught, then this is set countable, na. So this gives n cross n is countable. This is current alpha naught. Okay. Alpha naught and c are you can say cardinal number. Okay. Now if you make n times product, similarly two product, na. So if you make n times product of n, this gives again alpha naught power n, because its current will be alpha naught using this formula. Okay. So alpha naught power n is again alpha naught. So this is current alpha naught. So you can say this set is countable, na. Now if you take the product z cross z n times, this z n times product, okay, you can say. So if you make the product n times, so the current of z cross z will be current to power n. Okay, because z is current alpha naught, na, z is current alpha naught, each z is current alpha naught, because countable set, so current alpha naught, so current power n is again alpha naught. Okay. So if you make the n times product of q, then it will give current to power q, and current q is alpha naught, so current power n, alpha power n is again alpha naught. Okay, if it alpha power n is finite element, na, so it gives again alpha naught. But if it is not finite, then giving quantum. Now if you make infinite product, you can say alpha naught times n cross n, not finite time, alpha naught times. So this is current n, current alpha naught times. So current will be alpha naught, this will be alpha naught times. So this gives alpha naught per alpha naught. Now alpha naught per alpha naught will be 2 per alpha naught, na, because if you apply the word this alpha to beta equal 2 per beta, when alpha to beta, here alpha beta both are alpha naught. So this gives alpha naught and alpha naught will be 2 per alpha naught, and 2 per alpha naught is quantum. So this is countable set, na. So this is uncountable. So if you make countable product of alpha naught, you can say infinite product of n, then it again uncountable set. Similarly, you can make infinite product of q cross q, then it again uncountable set. Similarly, if you make infinite product of z, then it again uncountable set. Okay, hope you understand my point. Are you getting my point or not? Okay, so this solvable example of product. Now see this example. S is the set of all open interval, is the those open interval which is the coordinate decimal. Okay, we set of all open interval which is coordinate decimal. So you can, first coordinate coming for q, this second coordinate coming for q, na. So this set will be nothing but q cross q. Okay, because we know this a cross b is nothing but the set of all point a comma b. Okay, so that first coordinate coming for a and second coordinate coming for b. So if it coming from q, set will be what, q cross q, na. Now q is countable, so it is finite product, na. So finite product countable is countable, so this is countable set. Okay, now if it is the set of all polynomial a0 n to nx, okay, where each coefficient is rational. Okay, this set you can say is equivalent or equivalent to set this q cross q with n times. Okay, you can get a Bayes mapping from this set. Okay, if you consider the mapping, suppose if you consider mapping g from s to this set q cross q, and mapping is this s from s is a set of all polynomial, so px with this a0 a1 a2, you can say an, where px is nothing but this a0 plus an is 1. Okay, n is 1. Okay, so this map s is the set of all polynomial with coefficient rational. Okay, and if you take the coordinate rational coordinate, if you take the coefficient a0 n to n in the bracket, means this is a member of q cross q, you can say n times. Okay, so this gives a Bayesian. Okay, this is a Bayes mapping, you can clearly check it. Okay, it's Hadid is no doubt, because if you want to compute it, image. Okay, first of all, if you want to compute image g, so what will be image g? Image g is nothing but, you can say g of px such that px belongs to, you can say coefficient are rational number na. So yes, base belongs to qx set of polynomial with having rational coordinate. Okay, so g px is nothing but a0 plus a1x and an x to n. Okay, where each a rational, where a rational na, for all I equal to 0 1 to so on n. Okay, you can say no, this is nothing but this a0 a1, you can say an. Okay, where each I are rational number for all I equal to 0 1 to so n na. So you can say this is nothing but the set q cross q. Okay, so image is not q cross q, so image is equal to codomain na of the map. So image is equal to codomain, you can say. So this map is on to, okay, means Sagittarius map. Okay, also you can check clearly this map is on. Okay, no doubt this map is clearly on, because if you take two polynomial px a0 plus a1x and an x to n, okay, belongs to qx, means each coefficient rational a0 n to n. Okay, and if you take another polynomial qx, you can say qx equal to b0 b1x, you can say bn x to n, okay, belongs to rational qx. Okay, with such that g of p equal to g of q. Then what will be equal to 7? Then this g p is what coordinate of p, means a0 a1 a2 n, this will be equal to b0 b1, you can say bn na. So this mathematical coordinate will be usually equal. So this is a0 equal to b0, you can say a1 equal to b1, you say an equal to bn. Okay, so from here you can say g is injective also, means g is on also. Okay, so g is on and on to, so g is bijective map na, this is bijective. So you can say this set set of all mapping with coordinate rational, and this set are equivalent, both set of coordinate same. Okay, hope you understand my point. Okay, now we will discuss almost all theory regarding the chapter Countable and Uncountibility. Okay, if you have anything left, you can check out the book. Okay, any standard book, you can say. So I am writing one more important result, and after I will close this video. Okay, and tomorrow onward we will start discussing theory and question of point set topology. Okay, I am writing some important result with cardinal number. Okay, there is an important theorem. Hope you know this. This theorem is called continuum. Sorry, Cantor. This is called Cantor's continuum hypothesis. What does this say? This says, we know there are two cardinal numbers, right? One is aleph naught. This is coordinate of, you can say n, or any counter set. This continuum, you can say this is coordinate of r. Okay, so in between there are no cardinal number. The is cardinal number. Aleph naught is cardinal number, continuum is cardinal number. Okay, so in between them there are no cardinal number. Okay, there are only two cardinal number in all. Okay, there are two cardinal number in all. One is aleph naught, one is c. If it's countable, suppose a set is countable. If it's countable, then it's coordinate will be aleph naught. And if it's uncountable, then this coordinate will be, if it's uncountable, the coordinate will be continuum. Okay, in between there are no coordinate. Aleph naught and c, there between aleph naught and c there are no coordinate. Then no coordinate exists. There doesn't exist a set which having coordinate in between aleph naught and c. I am saying that there does not exist any set B such that which coordinate is greater than aleph naught and less than continuum. Okay, such set doesn't exist. Okay, this also there are some also the important result of sum. Okay, you can say aleph naught. This is if you consider coordinate of natural number, this is aleph naught. Then the important result of sum. alif node per alif node, you make it sum, find num quantity. You can say find sum. Okay, you make it n sum, n times sum. This gives n alif node. Okay, and n alif node equal to alif node again. Now you make for sum alif node alif node alif node, so on. This sum is alif node times, you can say count element times. So this gives alif node into alif node. Okay, so again alif node means it is also countable. Okay, but if you make this C quantum is current of R, or you can say quantum current of uncounted set. C plus C find many times, you can say it is n times. So it is n into C, again C means uncountable. Okay, so if you make infinite part C plus C uncountable part C times uncountable times C times, so this gives C into C, this is again C. Okay, this is again uncountable. Okay, now hope you understand my point. Okay, hopefully you know this result. I have written many times. 2 per alpha naught quantum will be equal to C. You can say 2 per alpha naught is current of natural number and equal to current of real number. Okay, 2 per alpha naught equal to C. 2 per alpha naught C. This is another important result. Also there are also one is one result. You can say C per alpha naught. Sorry, you can write this C per alpha naught means quantum per alpha naught. The quantum is 2 per alpha naught na, and alpha naught, so you have to write this alpha naught cross alpha naught means 2 per alpha naught square. 2 per alpha naught is alpha naught square is nothing but alpha naught. 2 per alpha naught is quantum. Okay, so you can say C per alpha naught. If you make C this C per alpha naught, this gives again quantum. Okay, I prove this. Okay, so hopefully I have discussed all theory regarding countable and uncountable, and tomorrow onward we will discuss question of points of topology. Okay, if you need doubt, you can always ask in the comment section. Okay, if anything left, you can check out the book. Okay, if I go to discuss all theory, then it will take a lot of time. Okay, and I can't solve problems CSIR-NET, so I have discussed almost theory that I have needed, and from tomorrow onward we will discuss the next chapter. Okay, so thank you. Please subscribe my channel and follow my channel. If hopefully you get many things here. Okay, to learn. Okay, so wait, I am discussing just on TIFR question. There are one TIFR question. Okay, see, just one question. This question asks in, I am writing this question TIFR 2030. Okay, this question said that is the settable sequence. You can say settable sequence is mapping from natural number. This is the settable sequences with n to n, which each entry means 0 1. Each entry has 0 1. Okay, so what is the cardinality? Okay, it's two for side question. It's saying it is countable. Okay, so either true or false. Okay, the question was not in format. Okay, I have written in format for my convenience. The question was actually in this format. Question was this. In TIFR, the question was this. Let S be the set of all sequences. Is the set of all sequences. You can say A1, A2, AN. Okay, where each AI is either 0 or 1. Each AI is 0, then S is countable. Okay, this is a question, actual question. Is the set of all sequences where each entry is 0 1. So sequences, so is nothing but mapping from natural number to a set. Now you say each entry is 0 1, so code will be 0 1, right? So each set is countable and uncountable. Okay, this is true false side question. Okay, we discussed many times in the previous video. Okay, so it's not for tough for you. You can discuss. You take it A and take it B. Okay, and you have to tell me in the comment section. Okay, please tell me in the comment section what will be the answer of it. Comment section. Either is it true or is it false? Okay, comment please. In the question I am giving you homework. Please tell me this question answer. Okay, what is your answer? Is true or false? Okay, it's question of TIFR 2013. Okay, true or false question. Okay, I have discussed many times. If you comment me, I'll know that I will not see my video properly. Okay, so there also one more question. I have given homework. Okay, question 2. This question of TIFR 2010. Okay, here's a question. The total number of subset. This question is this: total number of subset of a set. Total number of subset of a set containing 6 elements. Okay, the 720 option. 720. Second option is 6 to 6. Third option is 21, and fourth option is none of the above. Okay, this is another homework. Okay, you have to tell me the answer in the comment section. Okay, so please tell me answer of this in the comment section. Comment me what is the answer. It question says that total number of subset of a set containing a 6 element. Okay, I have discussed this theory in the previous lecture. Okay, almost many lectures I have discussed this theory. Okay, you will easily solve this question. It says that total number of subset of a set containing 6 elements. Suppose A with a set, so A is containing 6 elements. So it's saying that total number of subset means in power set. How many element in the power set? Okay, how many element in the power set? Okay, you have to tell this. Okay, so please solve this and tell me in the comment section. Okay, if you get this, I'll think that you will see my video properly. Okay, so don't worry, I'll give many solutions in the upcoming videos. Okay, and from the next video we'll discuss next chapter. Okay, and I believe this is enough for this chapter. Okay, so I'm closing this video. So thank you for watching and thank you.